jump right in with our definition. Let f of x, y, z be a vector field with a 3-component output in R3, and let our surface S be parameterized by our capital phi of uv. This parameterized surface is going to be just like the surface parameterizations that we saw in 16.4. Then we have a definition here, the vector surface integral, as opposed to what we saw previously where our functions were not vector valued functions. So this notation is saying this is a generic way of writing a vector surface integral, and this is how we compute it. We compute it by taking f of our surface as parameterized by phi, and dot that with the normal vector n of uv dv du. This is the way that we compute vector surface integrals. So I'm going to put a box around it. And a couple of things to point out. Recall that our normal vector, n of uv, is going to be computed the exact same way that we computed it previously. It's going to be our partial derivative of our phi function with respect to u, crossed with our partial derivative of our phi function with respect to v. And those two, the cross product is going to give us something perpendicular to our parameterized surface, which is our normal vector. And similarly, when I take my phi function and plug it into my f function, I'm going to get out some vector, and so it makes sense that I would dot this vector with this vector. And when you take the dot product of two vectors, you end up with a scalar that you can take the double integral over. One other comment, the bounds are going to be in terms of u and v, where u and v are the things that are parameterizing our surface. And these bounds can be represented by constants if our surface has those constant bounds, but we could also do a type 1 or a type 2 region in terms of u and v. So let's look at the geometry. What is this talking about, right? This is a great formula, and I'll do a couple of examples computing using this formula. Let's step over here and see some geometry. So let's say that our vector field in 3 dimensions, this is my 3-dimensional plot of a vector field, which is just crazy because I can't actually draw that, given by f. That's what those green arrows are. And let's say that I have some surface. Again, this is the only way that I know how to draw a surface. This is my surface S, and we parameterize our surface by phi of uv, which is going to be all these little grid lines that go along our uv surface. So this is our surface, and we want to know really what is going on here. I'm evaluating my vector field f along my surface. So I'm actually, at any point on the surface, I'm asking myself, what vector is coming out of this surface for any of the points here on this surface? And then the second part is I'm looking at that dot product with my normal vector to this surface. So recall last time that when I take my tu and my tv and take the cross product of those, that gives me my normal vector to the surface. And maybe I'll represent this as my normal vector. And of course, these normal vectors sort of shift in direction as my surface curves. And this dot product is measuring the amount of flow through the surface in the direction of the normal vector. So I'm looking at how much of my vector field vectors are pointing in the direction of each of my normal vectors. I'll write that down in real world language. What is my surface integral measuring? So what is my vector surface integral measuring? It measures the flow rate across S by this vector field. So I can see that my normal vectors are pointing this way, and I want to know how much of this vector field is flowing through my surface, the volume of that flow rate per unit of time. So another way that we call this is the outward flux. That's another word to describe this measurement, the measurement of the flow rate through this surface given by the flow of F. This is something that's sort of hard to visualize, but you could picture, like if this were a 3-dimensional lake or something, maybe a 3-dimensional river, and you had some fisherman's net, and you wanted to measure, the net might be some curved surface, right, that's bridging this river. And you want to know how much fluid is flowing across this net per unit of time. Well, it's essentially the measurement of this vector surface integral. That's exactly what it's measuring, because at each little place, we're seeing how much of the flow is going in the direction of the normal vector of the surface. And this gets to the next point, which is the orientation of the surface and why that matters. So the orientation of a surface with parameterization phi is given by the direction of the normal vectors. Because you can imagine that this is the surface, but with some other type of parameterization, I might be able to parameterize this so that my normal vectors were pointing in the opposite direction. It could still describe all of the points in space, but when I take that cross product, it really makes a difference which direction my normal vectors are pointing. In this picture, my vector field has sort of an upward motion, and it also looks like my normal vectors are pointing up and out as well. And so it means that in this case, the amount of flow, or the measurement of my vector surface integral, would be something that was positive. But you can imagine that instead of having upward pointing normal vectors, if all of my normal vectors were sort of pointing downwards from this surface, then in that case, my vector, or my fluid flow would be negative, and my vector surface integral would have a negative value. So unlike surface integrals where you're taking them over real valued functions where it didn't matter which way the normal vector was pointing, for surface integrals over vector fields, it definitely matters which way our normal vector is pointing. So that's something that we're going to keep track of. And in general, if you compute a normal vector and you feel like it's pointing the wrong directions for the physics of the situation, you can always flip it around by multiplying it by -1. Each of the components by -1 will just flip your normal vector in the opposite direction. That's sort of a minor point.